Hello and welcome back. This is Future Wizard, so the video will start normally here in a few minutes, but I had to change the format from my initial plans, so I'm just letting you guys know what's going on with a new introduction. This is a 465B that I wanted to do a restoration on and show everybody who follows the channel. We've been doing a lot of 7000 series stuff. I wanted to do some 400 series stuff, so I figured we'd do one of the most popular scopes of all time, a 465. My goal was to do the entire video in one shot, do the entire calibration on the scope, get everything finished up, polished up, and have a video for YouTube. This ended up being way more in-depth restoration than I was expecting. So I'm actually going to split it into 4 parts. I'm doing the restoration. I'm actually about halfway through it. But I'm halfway through it, and I've already shot 4 hours worth of video. So what I'm going to do is I'm going to split it up into 4 sections. We're going to do power supply and tube. So that'll be the first section, the calibration. Second section is the vertical section. I'll do that as a video. Then I'll do the triggering as a video, and then I'll do the time base as a 4th video. So split it into 4 videos. I'm about halfway done. That being said, on with the show. Hello and welcome back to the lab. On the bench today, fresh out of the box, we have our next project for restoration, which is going to be a Tektronix 465B. Have no idea what's wrong with this. It was powered up when I saw the listing. Did not look like it was functional, but it did look like it had all the knobs and everything on the front, so that's good. The other thing that intrigued me about this listing, this bag is in pretty rough shape, was this particular listing actually came with 3 tech probes. They're all the P6108s. I needed some probes for the lab. I've been looking for some reasonably priced tech probes. I have a lot of Tektronix plugins that I need probes for, so having 100 megahertz probes will be very beneficial for the lab. These will also work on the 7000 series, so be able to use those. But I've also got this 465B to restore. This one also came with the manual. Although the binding has seen better days over the years. I didn't notice it before, but this particular scope is serial number less than 50,000, so don't know if that's going to be crazy interesting or not getting into it, but we'll see what that means. It means in terms of a 465, it's a young scope. They made a whole bunch of these, but we'll see if we can't date it with some of the ICs and things that are in it. What we're going to do is we're going to take a look at this, evaluate it electrically, look at it physically, do a complete restoration on it, cleaning everything, and see what we can do to bring this thing back. This case is in pretty rough shape. Feet are busted. Case is all scratched up. The scope has seen better days. So, let's see, I'll give you guys a view of the back. Oh, we even have some friends. I got some cobwebs down here. See, fans should be here. We'll see what's going on there. Before I plug it in, I'm going to adjust this regulator because right now line power is running 119 volts. So I could plug it in safely there, but when I run it, I'm going to run it at the high regulation up to 132. So that'll be fine. Looks like Microdata in Irvine, California has owned this at one point in time. There's an asset tag on the back. I did see a Tektronix calibration sticker on the front here. See what that tells us. 91 was the last time this scope was calibrated, so quite some time ago. But let me get it plugged in, get it up off the bench, and we'll start this on the current limited supply just in case. I'll switch in a couple of extra bulbs to give me some more current, and then we'll see what happens when we put some power to it. Okay, I've got the current limit set up. We've got, bump this up a little bit. Okay, we're running about 118 volts, give or take. Give it a little bit more power before we turn it on. All right, we are running right about 119 volts now. Okay, I've got 2 amps of current limit switched in, so it's got, should have 2 amps of current at 119 volts before the bulbs kick in, roughly. Okay, we're down at 105, so we'll give it some more horsepower. All right, we're drawing right around 55 watts, and it's coming, ooh, okay, the screen's on, but, so we powered up, which is good, nothing crazy, 56 watts running, but we're now light on voltage, so let me turn this off, don't want to stress the power supply too much. Pull these bulbs out, and we'll put it on line power. So now we're into line power, no current bulbs in. And we will go ahead and... Okay, this kind of looks like it did from the vendor. Let's see if we can't get a sweep. So, bandwidth limit switch seems to respond. Channel 2 is off. Okay, I'm picking up some flickering, so it looks like we're sweeping. Where are we? Well, that's a good sign. The trace is moving. Position. Oh, hey, there we go. Graticular illumination is working. Throw these all the way up. Center these controls. On. Bring this way down. And hey, look at that. Okay. I have some indicators. Are these indicating probes? Watch these not be. No, they are not indicating probes. Darn. I do have one indicating probe. Okay, the indicator works. Channel 2. Indicator works. Awesome. Okay, so these aren't indicating probes, so I do need to get even different probes than this, but these are a good start. It's got a fragrance to it. Not like it's burning or anything, but, oh, okay, magnification was on. There we go. Okay. That is very loose. Gonna have to look at that. Yeah, look at that. Have to take a look at that. Position controls work. Yes, they do. How about channel 2? Position. Yep. Looks good. Beam finder work. It does. This is bent pretty badly, but it switches for now. I'll see if we can address that. Well, all in all, it's a great start. The tube, that's off. That's about a quarter brightness. So the tube is very healthy. Yep, tube is very healthy. All right, let's check if there's burn-in anywhere. Nope, phosphor looks healthy and uniform. So this actually looks to be in really good shape. I'm kind of worried about the positioning control on channel 1 now. So we definitely have some things we need to address in this scope. It is not the healthiest, but gives us something to fix. Yeah, positioning is dead. Next stop is opening it up, and let's take a look inside. Okay, I've got the feet off the back. They're pretty busted, tore up, so we'll be addressing those for sure. Power cord looks like in pretty good shape. Got a couple of furry friends down here. I've got the one screw undone that pulls the top case off. So let's see what we're getting into. Okay. It's gonna need some cleaning. All right, we'll keep going with the disassembly here. Let's see. That comes out. There should be, yep, screw on the bottom. Okay, for one of these 400 series, the back frame comes off. And then this pulls out of the power cord. I have to wash this power cord. This thing is dusty as hell. That's okay. We'll get that taken care of. We'll get this plastic cleaned up. And now you punch it out the front of the unit. So let me move the handle. I have not been inside this yet. We know at least it's not rocks because we saw a trace. However, let's find out what we're up against. That will be getting a bath. Maybe even a new case. All right. As with all the 400 series, it's pretty jam-packed in there. Transformer power supply section, it's kind of shedding. Yeah, this one's got ICs, so it's not all discrete. It does have some amplifiers in it. Dirt, but nothing too crusty. This is that pot that wasn't working. But that's weeble wobble, and I bet you we gotta. That may just be touching up a solder joint because that's working intermittently. Let's see, what do we got on the bottom? Familiar high voltage supply. Lots of adjustments. Nothing too crusty, actually. I don't see anything exploded or leaking. Vertical board, attenuator board, horizontal board, looks like. No, this may be part of the vertical amplifier. Horizontals over here. We have some caps. They look to be in reasonably good shape. We'll check them for ESR, and I'll also check the ripple, see how that's doing. If it's exceptionally high, we'll put some new cans in. Hopefully not. Definitely clean these BNCs. Eek. I am seeing some cracked solder joints, so we'll have to take care of that. Good news is nothing too awful, aside from some dirt. So I'll get into it. I'll start servicing some switches. Get everything patched up. That's a huge tantalum capacitor right there. He may be due up for a timely replacement. We'll see what he's doing. But yeah, nothing's screaming at me saying I've got problems. So we'll give it a very, very close inspection, and then we will we'll service up the controls, and then see what we can do on a calibration on this thing. See if it's got any other issues we have to take care of. I have the high voltage section removed. obviously this scope has been off for a while because I wouldn't stick my fingers in here when it was on. We have 6,000 volt rated capacitors. I cleaned up some of the dust and junk off of the cover and off of the components, just so we don't have any flashover. Got dusted the ceramic resistor. Still in process of servicing all the controls, getting everything going. Things are starting to feel like they should. Yeah, nice, positive, not dragging or crusty controls or anything like that. Everything's moving like it should. There was a little bit of dust in this area, but that's to be expected with the high voltage. Creates a little bit of static, so it kind of clings to it. I checked all the ESR on the bulk filters. Every single one of the bulk filters was below 0.02. So that's good. This guy is getting kind of high, so I'm going to replace him. And I'm going to see what I got. I might replace this cap as well. But his ESR was getting high, so I got to find a replacement for that. No, that's about it. Just doing some cleaning and dusting and getting everything, getting all the crud removed. Well, I'm going to let this sit for a little bit and put the cover back on, and if anything else interesting happens, I will bring you guys back. Okay, so I have done some preliminary work on the power supply and checked out a few things. Found a couple of bad parts already. This cap has been replaced, this cap has been replaced, and underneath this bundle of cable, if you're ever working on a 465, make sure you check this cap right here. That is a tantalum capacitor, and I don't know if you guys can see that, but that cap is corroded, cracked open, and is not healthy. That's the cap that was right back in here. So anytime you open up a 465, make sure you look at this one for sure. Make sure it's not blown open. These two just had a little bit of high ESR, so no big deal. I did some measurements on the power supply rails, resistances of the rails to ground, just in case anybody else is working on these power supplies. I've also checked the ripple voltages on all the supplies. These are the ripple voltages as checked at the capacitor, so 190 millivolts, but that's on the actual bulk cap. At the test point where you actually take the regulated voltages, so this is pre-regulated, this is after the regulated. The power supply rails are very, very clean. So what I'm going to do now is I'm going to get this flipped over. We'll get this turned back on, and we'll put some signals to it and see if we have any more problems. Channel 1. Okay. Well, it's tech gear. We know what that is. That's going to be cam switches. This is really loose, actually. No, the other one's, it's moving around a little bit, but too bad. So might just need to tighten up the bolts on that, but I can get it to come in. If I hold it, it goes away, comes in. I have the intensity of the tube really low. The tube is very healthy, so that's a quarter of the intensity control, so tube's in great shape. But at least we know the back half of channel 1 is working because I'm getting something through it. So I'll work on the attenuators. I've had some questions about those, so I will actually do that on camera. Let's check channel 2. All right, it is triggering. Move this. There we go. Huh. 0.2 doesn't want to work on channel 2 either. 20 does. Okay, so we have dirty attenuators in both channels. Not surprisingly, given the amount of dust that I've cleaned out of this thing so far. So let me pop open those attenuators and we will see what we can do about getting them serviced. Okay, so I've got the attenuator cover off, and immediately I see part of our problem. We have a friend, a spider silk. So we'll get him evicted. So the signal comes in from the BNC, goes into the coupling capacitor. This is the AC-DC coupling and shorting, AC-DC and ground switch. Then you have the 4 attenuator modules, 10x cut, 10x cut, 5x cut, and a 2x cut. And then there's a cam switch down at the bottom that has all of the attenuator switches. Now there's 10 millivolts per division, which goes right into the back of the FET, is on the back side of this board. So if that one needs to be cleaned, we may need to get back at this drum switch. Not quite sure about that yet. But what I'll do is I'll pull these out, and then I'll show you guys how I clean the attenuator switches. If we have to get further into it, we'll get further into it. Hopefully not. These sometimes are a pain to work on. But we'll do that, and then I'll also pull the cover off of this one. But let me get these. The way these attenuators come out is they just pop out, and these will get corroded pins. So these are nice and shiny, so those aren't bad. But let me pull off all the attenuators. Now it is very important that you maintain the order of these attenuators, because the indexing of the drum switch matches up with how the signal passes through the attenuators to get the proper attenuation. Because this is such a wideband amplifier, 100 megahertz, the gain is fixed. They don't adjust the gain of the amplifier. They attenuate the signal coming into the front end, so they have a set gain, which allows them to widen the bandwidth of the amplifier, and then the scale is how much signal goes into the front end. This is a delicate board material, as called out in all of the Tektronix manuals, so do not use any harsh solvents on these. No contact cleaner, no nothing. And these contacts are supposed to be kept dry, so nothing that'll leave a residue. I'm using isopropyl alcohol. It's 99%. But we'll just flood the area with alcohol. Obviously, when you're flooding the area with alcohol, the unit is off. Now I'll pick one of the attenuators that's down, and I will just gently rub the contacts back and forth. These have a self-cleaning action. When the switch goes down, it rubs the contact to clean them. So these actually suffer from disuse more than anything. You also have to be sure I am using a Q-tip, tapered double-headed cotton swab, but I like the not a lot of material because I'm using the soft of the cotton plus the stick to make it move just enough. And then rotate the cam switch. So you only want to clean the switches when they're in the down position, because these are a double-sided board. So when this switch is up, there's another one down on the bottom side. So you don't want to push down and then clean, because if you push down, you could break something on the other side of the board. This is probably one of the more fragile places of the scope. So it is definitely a place that you want to take care. But we did get some crap off. These are nice and making contact, so I don't think these need to be retensioned. I've had to do that on a few of my repairs, where I've gone in and retensioned the switches because they were sitting too high. They weren't actually making contact. I've even had to repair one of these leaf springs once to get it to push down hard enough on the switch. Alright, so we will be sure to let that dry. While we let that dry, I'll clean off our spider friend. Those pins look in good shape. They don't look like they're too crusty. Okay, let's put the attenuator back together. These are keyed, so you'll notice the pins are not equal distant. So these two pins are closer than these two pins. And that's the same for both sides. So you can only put these in one way, and don't force them, because they are fragile. Okay, before we put the cover back on, I'll bring you guys back down, and let's see if we made some improvements in that signal. Okay, it's Tech Gear. They're cam switches. Flushed it with the spray alcohol and moved the cam back and forth a whole bunch of times. And I have all the attenuators back. I'm moving the signal generator down so I don't overload the front end. There we go. They're all back. So I'm going to do the same trick for number 2, and I'll do the rubbing, and then hose everything down with alcohol and run the cam switches back and forth a few times. I actually was getting brown crap or dirt that was floating up onto the drum off of the cam switches, so this is what came off the backside of those cam switches, so definitely needed cleaning. Not good for the signal. It's happy again, so we'll do that for channel 2. If channel 1 needed it, channel 2 is gonna. Okay, well, I got this attenuator apart. I figured this was be a good time to explain how the front end of a tech scope works. So the attenuator module sits in between here, so you have signals coming this way through the attenuator module. So you have signal here, and attenuated signal would be at these points right here. The switches, as you rotate, you'll watch the switches move up and down. I'll do that now. So you can see how the switches change. Like right there, these two switches went down. When the switches are down, they're pulling signal up from the bottom side of the board, through the switch, into the attenuator, out of the attenuator, back to the bottom side of the board. There's a matching set of contacts on the bottom side of the board in the exact same positions. When an attenuator is not needed, it's bridged straight through from the front end to the signal. The output of the board's right here. So the way you can check an attenuator is, if you don't even need the scope. If you feed the signal in, if you pick up the signal right here, right before it hits this FET, then if you have signal here, the attenuator block is working. If you don't have signal here, it's getting lost in here. Usually it's these switches. With all the tech stuff that I've repaired and refurbished recently, I have not run into a bad attenuator. I have not run into a blown out attenuator. Now that's different on the 50 ohm stuff, because people have a tendency to not mind power limits on the 50 ohm stuff, and they'll put a transmitter right into the front end of their scope and just blow the front end of the plug-in. They can't handle it. They need a sampling T. But for these attenuators are pretty robust. I have not had an attenuator failure. I have had one where I've had the contacts in the attenuator needed to be fixed because they got loose. I had to make the spring a little stronger, but that's been a unique case. But yeah, so as I run there's one stop. So as I run it to the other stop, so that is no attenuation whatsoever. There's 2x, 4x, 10x, 10 and 2x, 10 and 4x, 10x, 10 and 2x, 10 and 4x, 10 and 10x, because remember this is 10x position, 10x position, 4x position, 2x position. In this scope, it's a 4x. In some scopes, like the 485, it's a 5x. And that's fully attenuated. So this is all dried up. I'll get all this stuff put back together, but that's how a tech front end works. Actually, I just got a good look at this attenuator. This one's not 10x. This is actually 100x. So that first position, instead of being 10x, it's 100x in the attenuator. So it's 100x. It's 100x, 10x, 4x, 2x. Okay, let's see if we have all our attenuators back on channel 2. Channel 2. We'll start at the high side. All right, hey. All right, there's 5 volts division. 2. Yep. 1. 0.5. Cut at 20 dB. And we have signal. Pull it down. Too much. Cut at another 20 dB. Got some noise in the frequency. And it's not the attenuator, it's just some noise. Yeah, that's the pot. Okay, it's not stable. Cool. So we got all our ranges back on channel 2 as well. So I'll put the shielding cover back on and get everything all patched back up. Okay, there's one other problem I'd like to address with this unit before we get too far into the calibration, or before we even start the calibration, is this control right here has taken an impact and the shaft is bent. So I'm going to see if I can bend it back. If I can bend it back and make it look right, then I'll leave it. If not, I think I have a pot that'll work, and we'll see where we go from there. Well, that straightened up a lot better than I thought it was going to, so it's like I bought one. Okay, I'm going to pull the implosion shield off in front of the unit. This has some gunk on it. I may end up resurfacing this. And while we're in here, we'll take a look at these, take a look at the graticule lights and see if we want to get these converted over to LEDs. I've done that conversion in a couple of scopes. There aren't any deep scratches in this, so everything looks pretty good. It's got the typical plastic scratches, so I'm not going to need to resurface this. If I was going to need to resurface this, I'd use emery paper on it, take it up through the grades. If anybody's interested in seeing that procedure, let me know. I will see if I can find an example of a screen that needs it. This has a black tape on it as a light dampener, so I want to be careful that I don't actually rub that off when I'm polishing the front of this piece of plastic, but I'll hit it with a buff wheel just to clean it up a little bit. The lamps on here are underneath this plastic. Let's see what they look like. Oh, they're not even dark. So when the lamps age, they'll get black, like a carbon on the inside. These are crystal clear. So at some point this scope will get LEDs, but these lamps have incredibly low time on them. There's not even any heat damage on this plastic. So yeah, these guys have incredibly low time. Don't know what the scope was used for, but it's in really, really good shape for as old as it is. So we'll just put that all back together, and then I'll buff up the implosion shield. So for cleaning the actual screens on these, I use a screen cleaner product. You want to be careful, especially with the modern computer screens and things like that, what you use to clean the screens, because if you don't use the right cleaner, the solvents will, the solvents will eat the coatings off the screens and make them look terrible. The trick is, the one you want to look out for is the ammonia that's in some glass cleaners. You don't want ammonia on any of the coatings on LCD screens or computer screens or anything like that, because it eats the coatings. I don't need to worry about wiping the graticule lights or graticule off, because on these picture tubes, the graticule is actually baked into the tube. It's not on the surface of the glass, it's actually in the glass. That's what makes it parallax free. So, just getting the fingerprints off. And that looks pretty good. So what I'll do is I'll buff up the implosion shield and then bring you guys back. I use a buffing wheel and a drill press to buff these up. But if you do that, you have to be careful with the speed of the drill press, because if it goes too fast, you can actually put burn marks in the plastic, and then you're into resurfacing. And so definitely try it with a sacrificial piece before you go on the unobtainium replacement part. And after a quick buff and clean, everything is good as new, as long as I don't hit it with a screwdriver and scratch it. Okay, so I have the display put back together. So we'll go ahead and turn on the unit. There we go. And we'll turn on channel 1 and channel 2. Look at that. Nice and clear. We have graticule lights. At initial glance, well, actually that was a pretty decent going through. So I'm at the point where I have to do an alignment on the scope, since we flushed out the attenuators and played around the power supply and things like that. The scope's going to need a full alignment before it can go up on the bench and be put into service. So what I'm going to do is, let me look into the service manual and figure out what that entails, and then I will bring you guys back. I have a plan. I'm going to see if it works. Okay, I think I have the scope all fixed up. Everything's ready to go. All the connections seem to be okay. So we should be ready to do a calibration on this one. So I'm going to use these tools, these terminators, those plugins, that scope, that meter, and my 8840 for the high voltage to calibrate this scope. So that's what's next on the list before we can put it into service. I brought the plugins down. These usually sit up here on the bench, so these are what I'm adjusting when, leveled sine wave generator, calibration generator, time mark generator. These are typically the three plugins I use when I'm working on. They've been warming up. I'm also going to fire up the Variac, because I'm going to need that for the power supply. There is one piece of gear that I don't have for this scope, and that is a CT3. I'm looking for one, but I don't have one yet. But from reading the calibration procedure, what that does is it puts an incredibly low-level signal into the scope so we can set the trigger points. That being the case, I do have a piece of gear that's going to sub in for that, my HP 8657A RF signal generator. I need 10 megahertz at about 20 millivolts. Right in the wheelhouse of the HP, so I got him warming up as well. I've been having some problems with some signals in the lab, and I found out This Terminator died. It's got a bad contact in it. It's just wore out from being used so much. So I will need to get another... God, I can't hold on to it right now. I will need to get another 50 ohm Terminator. Good ones of these aren't cheap. They're like 50, 60 bucks a piece. You can get them on Amazon, but if I'm going to be using them for calibrations and things like that, I want to stick with either the Tech brand ones or the Pomona or one of the other Amphenol, one of the other top tier brands. But geez, they're not cheap. I have 10x attenuators, which in dB, these are 10 dB attenuators. Just so happens that 10x matches up with 10 dB reduction. The 2x attenuators I haven't been able to find in the Tektronix version at all, but I have a couple of these. These are 6 dB attenuators to get 2 times signal reduction, because half of signal power is 3 dB. So a 2x reduction in signal is 6 dB. And then it also calls for 5 dB 5x attenuators, which rough math, these work out to be 7 dB attenuators. So I'm going to get some 7 dB attenuators, and then we'll compare the two, just make sure they're in the right ballpark to use. But for right now, I have the 5x. So 5x, 2x, 10x, and new 50 ohm through Terminator. So that's where we're at right now. I'm going to let this finish warming up. I got to let the scope warm up for about 30 minutes. And then we will get started doing the calibration on this. This is going to be a long video. This is a long process. This cal document's 40 pages, and it's double lines, 40 pages. So it's a long 40 pages. There's a lot of procedures in here. When I was doing the 7000 series scopes, I was able to split it up into 3 videos, doing the vertical section, doing the frame itself, doing the vertical section, and doing the time base. Because this is a 400 series, to do the full calibration on the instrument, we have to do all of them. So we'll start with essentially the frame, power supply, tube, get all of that lined up. Then we'll go into the vertical. Then we'll go into triggering. Then we'll go into time base and the timing. So it's going to be a long video. Unfortunately, there's not much I can do about that. It's just a long calibration procedure. So sit back, relax, and let's bring one back to life. Okay, while we wait for the scope to warm up, I figured I'd show you guys the adjustment interactions matrix. So this is a cool one that I haven't seen in a lot of service manuals yet. Basically, what it says is if you adjust the geometry, anywhere there's a black box, that will also have an effect. So if you adjust the geometry, it affects the y-axis alignment in the geometry. And so, but if you adjust the 55 volt supply, it affects everything in the instrument except for the CRT. So a lot of the adjustments only affect themselves, like the channel 1 variable balance only affects the channel 1 variable balance, doesn't affect anything else in the instrument. Change the CRT, it affects a bunch. Change the 55 volt supply, it affects everything. And then some sweeps, stuff in the horizontal affects itself, and then channel 1 and 2 affect themselves as well. There are different adjustments on the channels affect other things in the circuit. So kind of interesting to see when you tweak one thing, what else gets messed with. Main thing is this guy right here, 55 volt supply. If you touch that, everything's got to be done. Okay, to get started, this is after the preliminary controls are set up. This is the way to start the procedure, everything once it's set. I don't have the brightness turned on, but that's only because the tube's there and those controls don't matter. So those are fine. First things first is we check the power supply for regulation and test points. So Going to hook the meter up, then I'm going to turn the variac down to 104 volts. We'll check for proper regulation and for ripple on the power supply. At line voltage, we already know the power supply ripple's good. That'll stress the power supply a little bit, and if it's got any weakness, it'll show up there. Okay, here's the 55 volt test points. I'll be using this test point for ground for all of them. The power supply test points are right here. The high voltage is under here. We'll get to that shortly. Meter settings are 10 power line cycles with the filter on, so 10 power line cycles and then 10 readings for average. And currently I have 55.01 volts. So that's good. Let's bring this down to 104. Give the meter 2 cycles to catch up. That's actually in really good shape. It's still 55.01, so didn't even change when I brought the voltage down. Let me switch this over to AC. And we're still good on the ripple on the power supply. So I'm going to check the ripple here real quick on everything. So that's 55. That one's good. Yeah, that one's good. That's plus 15. Plus 5. Very good. Minus 8. Very good. 110. And that's good. So yeah, we are well in spec with the power supply. Everything is good there. I'm going to move you guys up to the meter. I'm going to do that same thing, but we will check the power supply regulation at low line voltage. So I'll move you guys up to the meter, and then I'll tell you where I'm moving the probes. I'm just going to do the exact same thing, but we'll check regulation. Okay, so as you guys can see from the meter setup, we have 10 power line cycles, filters on, auto zeros on, and we are at, well, the variac says we're at 104 volts AC, so the scope is plugged into the variac. Once I get done with the power supply testing, I'll move it to a power strip because then it'll be line voltage for the rest of it. But so that's the 55 volt rail plus 15. Oh, and my tolerance on this is 0.7%. So 5462 to 5539 is what I'm allowed up to. So well in spec. 15 volt rail is 1.7%. I'll got to give the meter a couple of times to stabilize. So this is, I'm allowed 14.75 to 15.26, 14.99, perfect. Plus 5's next. This one I'm allowed 1.7%, so 492 to 509. Excellent. I'm giving the meter, because it's set so slowly, I'm giving it a couple of times to stabilize. Next is -8. And I'm allowed 1.7%, so 7.86 to 8.14. Perfect. And plus 110. You guys can see what I'm waiting on as it counted up, because the first time it read 40, then it read 108. So I'm allowed 106.7 to 1133, plus minus 3%. We're at 108. That's perfect. Also bear in mind this is at low line level too, so this is driving the power supply of the scope at 104 volts, which I'm going to bump back up to full power here in a second. Okay, time to stay away from some test leads and use some things at well above their rated voltages. So what I have going on here is this is the test point for the CRT high voltage before it hits the multiplier, which is at 2,450 volts. Tolerance on that is 2.2%. The problem there is I don't want to hold stuff and fiddle with stuff and do stuff around the camera. So we have a meter lead that's rated to 1,000 volts that goes off. Everything is off at the moment. That goes off right here and connects to the front of the high voltage probe, which goes up to the fluke to do the high voltage measurement, because my fluke matches the HV probe the best. Ground of the high voltage probe. High voltage probe is back behind the scope. I will move you guys up to the meter and we'll turn the power on. Okay, remember this is a divide by 100 probe. So when I turn the power on, turn this on. My tolerance is 2396 to 2504. We are at 2,461 volts. So that is perfectly within spec. Everything is good. So we are done checking the power supply. Now, just so you guys can see, the scope is on. I'm going to turn that off. Going to unplug it because I don't feel like getting zapped today. And I'm waiting for everything to kind of discharge. The meter's telling me everything is good and discharged. I'm going to give it a little bit more time. Then I'll pull the probe off and pull the ground off and get the high voltage probe out of here. Okay, that should be enough time. Just pop this off. And here was my test setup. Here's the high voltage probe. It's just got a clip in the front end. But I was using this meter wire above its rated. This is only rated for 1,000 volts, so I was definitely getting some leakage current out of that, and I don't want to touch that. Overly cautious? Maybe, but don't feel like getting zapped today. Which leads me into one other safety element about doing one of these calibrations. All the adjustment points on this scope are open. We have voltages going everywhere. Line voltage is exposed right here. This is full 110 line voltage. This is where all the rectifiers are. Transformers down here. Line voltage switches back here. High voltage for the CRT is in here. There's a big red wire on the other side that's got 7 kV on it. But to do the adjustment, you got to flip this thing around. So the way I do it is I grab the front of the CRT, not the front of the CRT, but the bezel, and there's at the back of the CRT there's a good handhold that keeps your hands away from everything, and you can pick up the scope and rotate it and move it around as needed. The other thing you don't want to do is, because the cathode is so hot, or the heaters are so hot on the cathode element of the scope, you want to avoid physical shock to the scope, to the tube, while it's hot. It's just a longevity thing. You don't want to shock it. Okay, I have the preliminary controls set up for the display and Z-axis adjustments. One thing that's different is I have move the scope over to regular line power, but I have the regulating range set to high because it wants 115 volts line power, but we don't have 115 volts line power anymore. We're running about 120 volts line power. So that is something that this is dated, and you will want to have that set accordingly for your situation. That's what it looks like on the front, and we do want XY. That's a big change because we're going to be looking for a dot here in a minute, and On this one, gradical illumination needs to be off. Okay, here are the test points. Ground is again out here. This is TP 4217 in the hole. The bias adjustment is back here. So I need to turn this on and let the scope warm up again, and then we'll do the grid bias. If the grid bias isn't set right, it can very, very prematurely age the tube. Drives the tube way too hard. Okay, to do the grid bias, I need to turn up the intensity on the front of the unit to 20 volts. Now I'm going to dim the lights just so I can see it. Now what they're going to have me do, of course I dimmed the lights, now I need a flashlight so I can see the pot to put the adjustment tool in. We have a spot right here. Now we're a little high on the voltage, so we want to back it off just till the spot disappears. Okay, I need to do this one right in front of the scope, so let me move the camera, but that's what the grid bias is. Okay, so time for trace rotation. So 0.5 milliseconds. Okay, trace rotation's a little off. So it's even here, it's high here. So it's a tiny bit off, not much. So the trace rotation is just there we go. Okay. Again, the scope is still upside down, so I'm doing everything backwards. Okay, so we need the time mark generator. We need 1 millisecond time marks coming out into a 50 ohm BNC terminator. And then that gives us, I'll turn up the intensity. So the time marks are filling the screen. Hard to work on with the scope upside down. So as you can see, we have time marks. The time marks I have off the bottom of the screen, and then way up at the top. I want the time marks to fill the screen, and this is the top of the time marks right here. So the bottom is way off the screen this way, but here's the top. Using the position control, we want to line up the tops of the... Okay, this is off a little bit, because we want to do everything on this center marker. So I need to adjust R4072. This also has an interaction with trace rotation, so we'll have to go back and forth and check that a few times. Let me find the adjustment point and I'll be back. Okay, R4072 is this guy right here. So I'll get that lined up and then I'll show you guys what that looks like. Okay, here's the alignment. You guys are looking down at the screen like this, so the screen's tilted a little bit this way. These are pretty tight shots this way. So everything's lined up on the center graticule. I checked the trace rotation. It was slightly off, not too much interaction, so readjusted that, rechecked the Y alignment. So the Y alignment is good. We need to do geometry now, which is step 4. Okay, so the geometry adjustment is the bowing curvature this way on the screen, so an extreme bow this way. So as I adjust the geometry, the screen's going to kind of do this, spread out and compress. So I'm going to get right in line with it. I'm going to move the camera out of the way. The geometry adjustment is this pot right here. This is geometry. So I will get that adjusted and then I'll show you what that looks like when I get it done. Just to show you what an extremely detuned geometry is, if you look how the lines are bowing this way, it's an extremely detuned geometry. So I will, I'm still working on it. Okay, that's as good as I could get it, and I'm using the edges The further out you go, the more extreme the bowing gets. So I'm using the edges as reference, but you really want to use, you don't want to use the extreme edge of the tube. So you want to use this line and this line for reference, for graticule reference. So this guy and this one. So what is that, 2 and 9, I think, is what they are, but that looks good for geometry, so we are good there. And that has an interaction with the Y alignment, so we will also check Y alignment, and I may have to bounce back and forth and do that a few times. Yes, I did have to go back and forth a few times, but it only took a couple more times, and the adjustments were very, very small, so that all looks good there. Everything looks perfect, so we're going to take a look at the Z-axis compensation. Okay, here's the test setup for the Z-axis compensation. I have a well-compensated probe hooked up to the CRT test point. We're at 0.05 microseconds per division. And we are going into the Rigel. Okay, C4217 is hiding right here. This is our Z-axis compensation capacitor. It's hiding behind this ceramic resistor. So I need to adjust that for an optimum square corner for the unblanking pulse as viewed on the test oscilloscope. And they specify doing this with a low capacitance screwdriver. So I'll move over to the Rigel and so you guys can see what's being adjusted. And we're over at the Rigel. Nothing's changed. I'm looking at the square corner. This is really rounded off, so we're going to see if we can sharpen this up, but we want to sharpen this up with the least amount of ringing because we're going to look at ringing. I'm going to bring this down a bit. So, see what happens when we adjust our capacitor. Now that's actually pretty far out. Yeah, there we go. Starting to get some ringing. Yeah, see, that's what we don't want. And that's a good square corner. Actually, this circuit's pretty happy. Now we need to check for a uniform brightness across the display area. So let me get the test set up unhooked, and then I'll move you guys back to the screen. Okay, that looks to be uniform in brightness. Wants us to look specifically in these first two divisions for a uniform brightness across the trace, but it looks good to my eyes, so everything looks pretty set. Well, the adjustments seemed too easy. I didn't have the probe switched to 10x. It was on 1x. So I have to check the probe compensation, and I was measuring it at the wrong intensity. So I will have to redo that one. Okay, one more time with the correct settings on the probe. I am interested in this first corner. This is a much better step response, this is more of what I was expecting. So let's go ahead and tune that. Oh yeah, as I tune that capacitor down, you can see how it's adjusting the step response significantly. So we want the sharpest corner we can get, and that's too much. So right about there. And because you're seeing it raise just a little bit when I take the tuning tool off. So what I'm going to do is I'm going to adjust it down just a touch. So when I raise it, it's right where I want it, right there. There we go. So let's check the intensity again. I'll remove this probe. All right, turn this up. And we're looking for a uniform intensity across the display, especially in the first two divisions. We have it. That looks good. Thanks for stopping by the lab and taking a look at the first installment on getting this 465B off the ground. This is turning into being a much more in-depth restoration and troubleshooting process than I was expecting. So I'm going to have to break this up into a couple of videos. What I think is going to happen is part one is going to be what we just concluded, the power supply and tube section. Part two is going to be the vertical. Part three is going to be the trigger, and part four is going to be the horizontal. But we will see how it goes and how much this one wants to fight. So this is turning into a much deeper project than I was expecting, but we'll get there. So thanks for stopping by, and I will see you guys in the next video.